So should we go all non-parametric and that's just about it? Well, not so fast, say Flandin and Friston. In fact, sort of, their assessment of this very provocative paper by Eklund actually is, we're not impressed. It's hard to impress Carl Friston, probably. We're not impressed. Because look, think of it. Parametric inference based on spatial extent, so the Gaussian random field theory type cluster inference, it's invalid only when you use a low threshold. If you use a high threshold, it's perfectly valid. In fact, we already knew that. Says Carl Friston, I kind of said so in 1994 when I put out this approach. I very clearly specified that the expected value of the Euler characteristic is an approximation of the true limit only and only for high thresholds. Only for thresholds so high where you only get blobs and you don't get any holes, right? So if you have lower thresholds, the approximation where the expected value of the Euler characteristic approximates the probability of getting one or more clusters just by chance under the null, that approximation is only true for very high thresholds. So no surprise here, I told you so in 1994. Why is there such a big fuss? Furthermore, Flandin and Friston say, well, but look, there are many other reasons not to go non-parametric. First, the obvious reason, parametric analyses are statistically more powerful. If the hypotheses are met, and very clearly we know when the hypotheses are met, when you use a high threshold. So when the hypotheses are met, you're way better off with a parametric approach. True. On top of it, there's a certain aspect, parametric approaches are reproducible. If you rerun the analysis, you get the exact same t-statistic. There's no approximation that plays into parametric approaches. On the other hand, if you do a permutation type analysis, usually, they argue, you're not doing an exhaustive permutation. You're not really trying all the possible permutation. If you have 50, 60 subjects, it's going to take a very long time to do an exhaustive set of all the possible permutations. So it's likely that you're only doing this on smaller subsamples of permutations. For example, you're maybe only doing it on 5,000 or 10,000 permutations. You're not doing it on the full set of permutations, which could be really large. And then you have to do it for every voxel or every result. So if you were to rerun the same analysis, it's possible, the same threshold, and with a non-parametric approach, it's perfectly possible that just because you've sampled randomly a different subsample of all the possible permutations, your results could be slightly different. And sure, it's fair, it's totally possible, but as our computational power is increasing so much, I think we're probably gonna eventually converge towards being able to do exhaustive permutations, particularly if we can do it on a GPU the way Broccoli does. So I'm not sure for how long this point will still be valid. Now, on top of it, and this point will come again in the last piece that I want to show in this lecture, exchangeability, for exchangeability to hold, you need to have no covariance between your observations. And there are cases where you get serial correlation. Now, the obvious case would be when you're doing a time series analysis, but as I said, we just don't use this type of approach for time series analysis. However, what I think I made this example earlier, what if you do have, twins in your studies? Those observations will be whatever your analysis is, whatever your experiment is, where maybe one of the twins gets a certain manipulation and the other one acts as a control. There will be correlation in pairs. And so that breaks exchangeability. The FSL people, however, simply solved this with what they call exchangeability blocks, meaning you can tell the permutation software, say, look, keep in mind, there's this structure in there, so don't permute the twins, always permute across any of the pairs. And the same is true if you have a time series design, meaning you have a repeated measures design. You can tell FSL to only perform permutations within certain, what it calls exchangeability blocks. So this is also fair criticism. However, I think we're getting around it. And finally, parametric methods are computationally more efficient than non-parametric. Of course they are. It takes a millisecond to do a t-test. However, it's also true that our computational power keeps growing. So again, I still don't think this will be a hard problem. So finally, their view is, sure, if and when the hypothesis of the random field theory or sort of parametric approaches are not held, sure, then you might, perhaps, maybe consider using a non-parametric test. I don't share this negativity on it, but you should make up your own mind. Finally, the last part I want to add to this before closing with a little food for thought is this wonderful paper by Helwig in 2019 discussing the fact that saying that non-parametric, so permutation type analysis, only require exchangeability is actually not strictly true. They also require a symmetric distribution of the test statistic. So they require something symmetric, kind of like a normal or like a logistic. Even a uniform is perfectly fine, or a Laplacian. But if you get something where you have a skew, then the problem is that when you sample the skewed part of the distribution, then you risk pulling your resampling distribution in awkward ways, and that can hurt the distribution, the resampling distribution. So the non-parametric, essentially the non-parametric machinery. And that can lead into funky results, which can hurt your ability to enforce the proper error rate. In fact, so what Helwig did, it was a number of different distributions. It's a wonderful paper that did a lot of different things. I just want to give the main message of it. And so they took a statistic, he took a statistic from all of these possible distributions, and then reported for different samples the error rate, and reported the error rate for both a t-test and a permutation test. And sure enough, when you use a symmetric distribution, when the statistic that you're resampling comes from a normal distribution, and this I think is a regular one sample t-test, you get the appropriate 0.05 error rate. And this is true both for the t-test statistic, which is in red, and the permutation approach. And the same is true for the Laplacian, the logistic, and the uniform. So anytime you have a symmetric centered on 0, then you do truly get a good control on the error rate. The problem is when you get a skew. And when you get a skew, you actually get either inflation, here in the case of a left skew, or a deflation of your error rate, meaning you can either get sort of pretty inflated values. I have to point out, this is nothing compared to the amount of inflation that we get. I mean, we're talking about 0.08 compared to, you know, to the 70, 80% that we got with other techniques. So just saying that we only require exchangeability is strictly not true. There are a number of other things that are necessary to be assumed. And however, it seems to me that even under these conditions, it's not a big deal, particularly if you don't use 10 subjects as your sample.